We'll go ahead and get started. So thank you everyone and welcome to the joint NISS and CANSSI Collaborative Data Science webinar. I first want to give a shout out, thank you to the National Institute for Statistical Sciences and the Canadian Statistical Sciences Institute for sponsoring this web series. The goal of this series is to showcase experts from various fields who tackle complex data challenges through interdisciplinary teamwork. And so for each one of the talks in this series, we have collaborators, one from data science and one from a expert in a particular area of science. So I am Emily Casleton. I'm a statistician at Los Alamos National Lab, and I chair the organizing committee for this web series. So one thing I wanted to say is if you have an idea for this web series, maybe even yourself, please feel free to reach out to me, and we can bring it up with the committee. So this is only the second talk in this series, so a lot of thanks to our speakers for being kind of guinea pigs in this. Our next one will be on Thursday, May 8th, and it'll be on AI for health data. And if you go to the NISS website, you can see the announcement for that. So that's all I'm going to say about the whole web series. Now we'll get to what we're actually going to talk about today. So I'm really excited to have our two speakers here today, Kelly Moran, who is also an applied statistician at Los Alamos National Lab, and Katrin Heitmann, who is a physicist and computational scientist at Argonne National Lab. They're going to talk to us today about astronomy and cosmic emulation. And I wanted to mention that while they're talking, if you have questions, if you could please put them into the Q&A. I'll try to kind of monitor them. If there's a natural break, I'll either call on you to read it or I will read it aloud for you. And Kelly and Katrin will kind of also look at it while they're not speaking and see if they can answer it. So put your questions there. We'll try to navigate getting them answered. And so that's all from me. So go ahead and take it away.
You should be able to see this. So Kelly and I are really, really excited to have this opportunity to talk to you. And the way how we structure the talk is you hear a little bit about cosmology, then you hear a little bit about stats, and a little bit more about cosmology, and a little bit more about stats. And so I'm going to start with a really, really quick introduction to cosmology and giving you an overview what our project that we are working on together is all about. And let me start with this. Cosmology is all about making maps. So usually when you're a physicist, you have a certain question that you want to answer and you build an experiment. That experiment can be small, tabletop, it can be really big, like the Large Hadron Collider in Switzerland. But in cosmology, you can't build really experiments. So what we do instead, we are observing the universe. And since we only have one universe, we want to observe it in as many different ways as possible, and then try to actually come to a picture about the makeup of the universe and the evolution of the universe. How did it start? Sometimes we also look a little bit in how will it end. So that's kind of fun. We will be very, very lonely, I can tell you that. And you see here 4 different maps in different wave bands. So what we are trying to do is to look at the universe in different wave bands with different instruments. So the instruments are on the bottom here on the right. And we are mostly going to talk about optical surveys. So we'll get into this a little bit more. So the maps that we are actually making, they cover objects, stars and galaxies, as well as fields. So you see here on the right some temperature maps. And they can be very, very large. As an example, I will talk about this a little bit more. The Rubin Observatory, which is going to start taking data this year. It's really exciting. We prepared for that for like 20 years. They will catalog 37 billion stars and galaxies. And so you can imagine that statistics plays a very, very important role here. So basically what we are doing is we are doing a statistical analysis of these maps, and we are going to talk about this in the next hour. And basically it's a large statistical inverse problem that we then have to solve. And as you can also imagine, is these maps are very, very complex, and large-scale simulations play a key role there. So we'll talk about this as well. And the very first thing I want to talk about is what are the questions that we are asking. And I can talk about the slide for an hour. I will try to keep it to 5 minutes. But there are really big questions that we want to answer. We have discovered in the last 30 years, we have built something that we are calling the standard model of cosmology. And we discovered that 95% of the universe is dark. So the energy matter content of the universe is dark energy and dark matter. And I'll talk about this a little bit more. And we don't understand the physics of it. We know it's there, but we don't understand the physics of it. Let's walk a little bit slowly through this diagram. So 69% of the universe is in something we call dark energy. How can you think about that? I think a very nice analogy is, so I live in Chicago. Chicago is very, very flat, and you can bicycle on the Lakeshore Front Trail. And suppose it's really, really flat, no ups and downs, and you're bicycling, and let's forget about friction. And so you have some speed and you stop pedaling, and you should just coast because it's flat, right? But what you actually experience is that you are speeding up. So something in your picture is wrong, right? Either you are wrong that the trail is actually completely flat, it has a little bit of a curvature, or somebody is actually sitting behind you and pedaling and you don't know about this person. And both of them are kind of like puzzling things, but this is basically what we discovered in 1998, when I say we, the community, when we measured how the universe is expanding and how fast objects move away from us. What the team set out at the time to prove is actually that this flatness idea that, yes, the Lakeshore Trail is flat, but what they discovered is that we are accelerating. The expansion of the universe is accelerating. So things move faster away from us than we expected. This was a huge, huge surprise to everybody. It was a Nobel Prize later on for the two teams who first discovered this. And what we want to understand as cosmologists is exactly what I said before. Is there somebody pushing us, which would be a dark energy? Or is there actually a curvature in our trail where we are bicycling on, which would be a change in Einstein's theory of general relativity on the very largest scale? So there would be additional terms in the geometry. So this is what we are asking. And it's we are building really extraordinary instruments to get a handle on this. And so this is the first big puzzle. The second big puzzle is this other 30% of the universe that's in something we call dark matter. So if we go to the second pie chart here, you see that 80% of the total matter is actually in dark matter. So only 5% of the universe's matter energy content is in visible matter. So we call it dark matter because it doesn't emit or absorb light. We know it's there from observations that are indirect. So we see that the light, for example, in the universe, if we look at a faraway galaxy, we see that the light that comes to us is bent because it hits large matter clumps in between us and this galaxy. So we have a lot of indirect evidence, but we don't know, again, what the physics is. We have built very, very large detectors, and we hope that the dark matter will hit these detectors and tell us something about their particle nature. But so far, we haven't succeeded in that. So there's another very big puzzle. What is the nature of dark matter? How does it fit into our understanding of particle physics, for example? Another big puzzle is the neutrino. So the neutrino is something that is, so you're being hit right now as you listen to this talk by gazillions of neutrinos. They just zoom through your body. And they are particles that are very, very light. And I think it's super exciting, awesome, however you want to put it. But the distribution of galaxies in the universe actually tells us something about the mass of these neutrinos. Originally, when the neutrino was invented a long time ago, and by the way, Los Alamos got the Nobel Prize when it was actually detected a long time ago for the detection of the neutrino. Originally, it was thought the neutrino is massless, but by now we know it has a very, very small mass, but we don't have exactly the number for this mass. So another big puzzle, and cosmology can help with this. And then the last one I want to say is, what is the physics of the very early universe? How did it all start? Again, something where we have an idea, but we want to know much more. What is the physics? And so a lot of this information, or all of this information, we actually get from these maps that I mentioned before. And I'm talking a little bit too slow. I knew I would spend too much time on that slide. But the second part that we have really gotten a better understanding from these maps is the evolution of the universe. So here you see a timeline of the universe. So it starts very early on, 10 to the minus 33 seconds after the Big Bang. Everything was very dense, hot, and started expanding. So you see at the beginning, this cosmic inflation, this is the phase that we want to understand much better from, again, these maps that we are collecting. Then you have a phase in the universe, which we call the dark ages. So there were no galaxies there. It was too early for them to form. We can see that. And then we have this phase where actually galaxies start forming. And you have heard maybe of JWST, the James Webb Telescope, which is actually right now taking observations of the very earliest galaxies. So that's very, very exciting. And from the distribution of galaxies and from observations of the very first galaxies, we can learn a lot more about the universe. So this is like, as I said, I can talk about it for at least an hour, but we don't have that time because Kelly also wants to talk about the stats part. So this is very, very short, and I'm happy to answer any questions on this that you might have. So I am working mostly with optical cosmic surveys, so I'm focusing on that mostly here. And here are two surveys that are actually ongoing right now. So on the lower left, you see the dark energy spectroscopic instrument, or DESI for short. DESI just in May we are only in April. In March at the APS meeting had a big splash. So they have some results on possibly some hints on what the nature of the dark energy is. So everybody is very excited about that. So what DESI is doing is it's creating a 3D map of the cosmos and mapping out the distribution of galaxies. It's ongoing. It's in its third year of data taking, so that's very exciting. The second one that I am deeply involved in is the Vera Rubin Observatory. So this is a telescope in Chile. We finally managed to finish the telescope. Commissioning is ongoing. We will have the first photons on a humongous camera. The camera is as big as a small car at some point next week, if everything goes well. So that's really, really exciting. And then observations, map making starts later this year. So this is really, really cool. And then there are also space-based missions that I'm involved in. Spherix is a small satellite that just launched. So they started taking data a couple of months ago. And all of these, again, they are making maps for us that we have to interpret to get more information about the physics of the universe. This is just a fun picture. So this is actually data. So this is data from the Dark Energy Spectroscopic Survey, DESI, that I mentioned before. The different colors indicate different types of galaxies. We are sitting in the center of this and we are looking outwards. So if you see something further away from the center, it's actually further away in time as well. It's earlier in the universe. And this little zoom in here, you just see that the galaxies are not randomly distributed. And this pattern that we call the cosmic web is actually something that tells us a lot about cosmology. And again, you can imagine that statistics is very important when we want to try and interpret these patterns in detail. And one of the major statistical measurements that we are making is the power spectrum. And since Kelly is talking about this quite a bit in her piece, I want to dive into this a little bit. So the power spectrum is actually pretty easy to understand. So I live in real space, not in Fourier space. So the power spectrum is in Fourier space. So let's start with real space just to get our head around this. So the 2-point correlation function is the excess probability of finding an object pair separated by a distance R12 compared to that of a random distribution. So measuring the 2-point function is actually relatively straightforward in cosmology. And the power spectrum then is just the Fourier transform of the correlation function. And here in this picture, you actually see measurements of the power spectrum. So the black line is what we think is the correct theoretical model of the universe, which has the dark energy in it. It has a very simplified model of the dark matter in it. And the different colored points are from different experiments. So Planck is actually, it was a satellite mission that has finished. It measured the cosmic microwave background. And so different maps, so it's not really important what TTEE and Phi is. They are just different maps of a temperature. And so you can see they cover the left part of the power spectrum. So they give us information about the very large scales in the universe. The lower three, SDSS, BOSS, and DES, they are optical surveys, and they cover the right part. So just as I've been in this cosmology business for quite a while, that these measurements would actually match up as nicely as they do on these scales was not clear from the start. It was a big satisfactory finding that you can actually put them all on the power spectrum and you would have this nice lineup, and the black line, which is a theory curve, actually describes the data really well. So that was kind of a relief, because if they would not have been matching up, if they would have been offset, for example, we would have been really puzzled. So putting together this data was several decades of work, and it's really great. And Kelly will talk much more about the power spectrum next. One last thing that I quickly want to cover in a couple of minutes is now the simulations. I said at the beginning, in order to interpret these maps, we need large-scale simulations. We need as big supercomputers as we can get our hands on, because these maps are so big. You can imagine if I want to simulate 37 billion galaxies, it's a lot. And so supercomputing is a very important piece of that. So in order to do these simulations, we need the constituents. So I talked to you about this a little bit. So we need to have a model for the dark energy, for the dark matter. And for now, what we are assuming is that the baryons, the stuff that you and me are made of, are just following along the dark matter, and it's just gravitationally interacting. So there is no physics of the baryons in the simulations that we discussed in this first part. We are coming back to this in the second part of the talk, where we add some of the physics back in. But right now we are just saying everything, the most important force in the universe is gravity, and we are just focusing on that. You need initial conditions. So we have those from our observations. You need dynamical rules, that's the gravity piece. And then you need a big computer. On the right here, you see a couple of simulation results where you see again the cosmic web, where we have put in different physics, different ingredients, constituents into the simulation. So the first one, we just, we did everything as I explained to you on the first slide. We had 70% of a dark energy and a large amount of dark matter. And that was a cold dark matter, so the dark matter didn't have a temperature. In the second picture that you see, what's called warm dark matter here, we put in a temperature to the dark matter. So we said like the dark matter, we just made that up. We said like maybe it has a temperature, what happens to our cosmic web? And what you can see is in the simulation that it's much smoother, right? And so now you can imagine if I compare this to my observations, I can actually say something, how much of this temperature should be there. And then in the third one, we said there is no dark energy at all, and you see everything is much more clumpy. And again, you can measure that in the observations, you can compare to your predictions from the simulations, and then see, is there a dark energy or is there not? And before I hand over to Kelly, I want to show you one of the simulations again. So what we have here is a dark energy and a dark matter component. We have gravity in there. We neglect the neutrinos here. We can put them in as well. And we want to see how the universe evolves. So I show you here a little brick. So the one thing is that for numerical purposes, the expansion of the universe is taken out of the coordinate system, because otherwise you would go from very small numbers to very large numbers. And numerically, that's just unstable. So you just do a coordinate transformation to have everything in what we call co-moving coordinates. The number z at the bottom is a time that we love to use. It's redshift, doesn't really matter, but you will see it counts down. So at z of 0, we will be at the universe today. At the beginning, the universe was very smooth. So that is our initial condition that we measured from the cosmic microwave background. And what you will see in this movie is how gravity pulls things together. And let me just play this. So we are just moving in a little bit so that you can see what's happening. And so you see time is running forward, z is getting smaller and smaller. And now you see these structures are forming. And what you will see is that, so you have very small perturbations at the start. and they build up. They accrete more and more matter, so gravity starts forming these clumps, and now you see how the cosmic web is actually forming. And so we are almost at the end. So you see here this very big clump forming in the middle. We will zoom a little bit around that. And now again, you can see the clumps here, they are not randomly distributed. So if I want to do cosmology, I want to measure statistics on these clumps. I can measure how many are there, right? I can simply count them. I can do the 2-point correlation function on them. So these are all measurements that we can do and that we can then also do in the real universe. And I pause here because next I will, oh yeah, I have a summary so far. Sorry, I forgot that one. I know there was a lot of information in the first 15 minutes, but the universe is dark. We have many puzzles to solve. I think I convinced you about that. We are making maps of the universe in different wavebands, and we are measuring a range of statistics that tells us something about the components in the universe and its evolution. We have to compare our results to theoretical predictions, and simulations are really crucial for that. The next part where Kelly is going to talk about is the simulations are very, very expensive, and we can only do a few of them. How can we optimally use a few simulations to actually make some progress in this question, in all these questions that we ask at the start? And with that, I'm handing over to Kelly, but I'm also happy if there are like some super urgent questions to answer.
Okay. Yeah, thanks, Katrin. Every time I hear you talk about this, I'm reinvigorated with excitement for cosmology. But yeah, I'm going to be going into some of the details on how we're doing simulation design, smoothing, and emulation for this matter power spectrum that Katrin mentioned. And I'm going to jump forward to summarize the results of the tool that we ended up creating, and then I'm going to go back and describe the process by which we made this tool. So the tool that we've created to facilitate emulation of the power spectrum, which is to say a statistical approximation to these large-scale simulations of the power spectrum, is called the Cosmic EMU. It's useful in the case where people want to explore the space of cosmological parameters, but they say don't have time to wait multiple weeks to see what a given parameter setting looks like. If you want motivation for why you should listen to our overall method, this is showing the predictive performance of our method relative to other competing emulators. This middle line here says we're getting things perfect. Plus or minus 4% error is shown in the other two lines on the plot. And our emulator is this kind of bolded black line. And these are showing the results for a single test cosmology. To note, the percent error here is, sub 1%. And for the sort of suite of tests that we ran, we're ending up with less than like 2.5% error, which is quite good. And relative to competitor methods, we have a much broader set of the parameter space that we can explore. So our parameter ranges are wider. So all of this is just sort of saying, if you are intrigued by the results, you may be interested in the statistics that get there. So as Katrin mentioned, the first step in this process is running some amount of these high computational intensity simulations. And so then the question becomes, where do we run those simulations? So if you imagine the set of cosmological parameters of interest, asking where should we run the simulations is saying like what knobs should we turn and where should we turn them to when we're doing some set of like big theoretical runs. And the answer that we came up with is that we want to be able to have an interim set of simulations that fills the space fairly well, that we can start analyzing early and then continue to fill the space more densely in subsequent runs so that we are able to kind of have this interim check and also start publishing results and publishing a emulator that can be used while we improve its performance in successive years and efforts. So the way we did that is via this nested space filling design. So the idea here in 2D, if you look at the left half of this slide, is that we have a sort of honeycomb-esque representation of the space, and we can fill sort of a bigger set of honeycombs by placing here our dark blue dots evenly spread throughout this space. And then we can refine and increase the density of the points that we're looking at by making a smaller set of honeycombs kind of surrounding our current points and filling those in. So that allowed us to have a stop point. I think it was about a year in or so of our simulations, and to publish a preliminary emulator that we've since refined now that we have this full set of simulations. And our full set of simulations here, the red points here are our initial set, and the black points are our full set of 111 simulations. This is just shown the 2D projection onto the pair of our 8 parameters. So yeah, we don't have to focus on this, but this is just showing the visual result. And we have an additional set of runs with 0 neutrino mass to get at this sort of hypothesis that Katrin was suggesting that people had early on, that there wasn't, that the neutrinos were massless. Okay, so that was a breeze through the simulation case. We also, I should mention, have theoretic results for large distance scales in power spectrum land that says for low K values, we can say with theory, not with simulation, what's going to happen. And that on this left plot is shown as the black line. And then for sort of these smaller scales, that's where we need our simulation results. And I didn't touch on this when describing the simulations, but as part of the design, we included both lower resolution runs and a high resolution run as a way to get better resolution for this sort of middle region that we're interested in this plot. If you look at the spot where the red and the blue overlap, there's these wiggles. Katrin could describe better what that means, but that's related to like density fluctuations in the early universe. And Katrin, if I butchered that, correct me in the chat. So we're interested specifically in that zone. We have theory, we have high resolution, this blue line, and then we have a set of lower resolution simulations. What we want to do is we want to learn the underlying smooth matter power spectrum implied by theory, low res, and high res simulations, and that's this statistical combination step. So what this looks like, again, kind of jumping to the end of the story for this example power spectrum, which is a transformation of the scale that Katrin was showing, just to make it easier to emulate, is a smooth line that still is able to capture this baryonic acoustic oscillation region, this like wiggly middle. So how do we do that? Let me see if I can play this video. The intuition here is shown in this video. We have the ability to model a varying kernel width that changes over the domain of our function of interest. So if I play this again, if you watch the top, this is showing a kernel parameter that's smoothing these impulse functions, and it's allowing for more wiggles in the middle and less wiggles on the fringes. So our kernel's narrowing, we get wigglier in the middle, our kernel widens again, and we smooth out. And this is a generative model for the first layer of what we'll call a 2-layer or deep process convolution. So the generative model says we can draw a latent process. Here, that's these bars, these impulses, and then we can kernel smooth that process using a variable kernel width. So let's see. Okay, we can stop playing the video. The math behind this looks a little bit intimidating. I just wanted to show it for people that enjoy having equations. The intuition here, as we mentioned, is that we have this transformed matter power spectrum, smooth matter power spectrum, and we're modeling it as this convolution of impulses with a varying kernel bandwidth parameter. And the impulses are a realization of Brownian motion in our model. The kernel matrix has, like I said, varying bandwidth. And the reason this is deep, the reason it's 2 layers, is because we are modeling that varying bandwidth term as a process convolution as well. So we're not specifying, in the middle it needs to be wigglier. The model is able to learn that by learning this sigma term, this width term. Yeah, so this is showing some synthetic data and the results of using this deep process convolution model to learn the true function underlying synthetic data. So the settings are just sort of trying out different types of data. I think setting A is homoscedastic, and setting C looks a lot more like our data, where we have like known theory plus a few different resolutions. And the thing to note here is that this is just showing the mean squared error of our predictions of the functions. And our process convolution model is outperforming the kind of standard competitors that one may use to do something like this. So the competitors here are a GAM, a heteroscedastic GP, and a deep Gaussian process. And of note, we're outperforming those competitors for replicate simulations of these functions under these settings in pretty much every case. So it appears that this is a kind of method that, is very useful in this kind of special case where you have utility to sharing information about that kernel bandwidth across functions. Yeah, so now we're kind of in the final step. So we've done our simulating of things. We have a set of simulations. We've transformed them all into this emulation space. We've combined them so that we have one smooth power spectrum associated with each set of parameters, with each cosmology. And now the question is, okay, if I have a new cosmology, what does it look like? Or what does the power spectrum for that cosmology look like? And that's this emulator piece. So again, to skip ahead to the punchline before showing the details, this is the simulation, so the ground truth, and yellow is our emulator. They're dashed just because if they weren't, they would be pretty much entirely overlapped. So this is, again, showing that there seems to be something here that is doing well. Great. How do we actually do this? How do we predict at new cosmologies? So the foundation of the model that we use was originally published in a paper by Dave Higdon, who was on our team and is still involved in the project, that says we're going to, for functional realizations, do this process of centering, scaling the data, projecting it onto an orthogonal basis, and then modeling the basis weights with Gaussian processes. So for each basis weight, if you take a PC decomposition of your data, you will say, okay, great, for basis weight 1, I'm going to model it with a GP. For basis weight 2, I'm going to model it with a GP. Basis weight 3, and so on and so forth. And it's wrapped up in this big Bayesian model where there's some extra terms to kind of learn the behaviors of the Gaussian process and learn the precision of your overall principal component representation. So yeah, I mentioned modeling with a Gaussian process. What is a Gaussian process? This is something that many of you may be familiar with, but essentially a Gaussian process is a way to represent multivariate data as a multivariate normal distribution. So I think the like technical theoretic definition is that a GP is an infinite dimensional generalization of a multivariate normal distribution. But what that means in essence is just that you can describe the relationship between any two observations using this correlation function, which has some parameters that you can learn. So for example, you might say, you know, cosmology 1 and cosmology 2 are very close together in space. That means their correlation is high. And that means that you know that something close to one of those guys probably looks kind of like it. And the GP is just a way to formalize that idea with the associated like Bayesian magic of learning the parameters and having uncertainty baked in. So yeah, here's just a visual of kind of what Gaussian processes do. On the top is some unconditional Gaussian process draws. So if we say I'm going to sample from a Gaussian process and it has a certain smoothness, this is what it looks like on the top. Now, if I get to the middle, I say, okay, actually I observe certain points along the true function, here these red dots. Well, then once I condition on having observed those points, my Gaussian process draws look a lot more contained and reflect kind of the certainty about your value based on how close you are to an observation. So we can kind of see this like widening in between these 2 points, for example, and on the fringes of the data here. Yeah, so again, for people who like equations, we have our sort of simulation pieces, which are eta here, and we do a principal component decomposition. We say, okay, we're going to represent our observed power spectra, our like known simulated power spectra, as the sum of these principal component terms. There's some error associated with this if we're not using every single principal component. And now the GP bit is that for each of the weights, we're going to model these as multivariate normal with the Gaussian process correlation term. And yeah, that is kind of the big punchline. And this is implemented in Python as sepia. Some of the members of our group recoded some of the like annoying MATLAB implementation into a more user-friendly Python package, which was great. And yeah, to kind of zoom back in, now we've done this PC decomposition for each of our weights. We can say we observe where all of our existing cosmologies were in terms of this weight space. And for each weight, we can now predict what the value would be at the point in the cosmology space that we're curious about. And that gives us, once we multiply it back out by the principal component basis, this, in our case, very accurate way to predict new cosmologies, the power spectrum for new cosmologies. And I think that's back to Katrin for a bit, but if anyone has any questions, I know this was also kind of whirlwindy. I'm happy to follow up in the Q&A or answer them now.
Okay, let's continue if there are no immediate questions. And you might remember that I said at some point before I handed over to Kelly that we didn't have all the physics of the universe in the simulations. So what Kelly had just showed us is how to emulate the power spectrum if we just include the gravitational forces. But now let's look a little bit further. And so here what you see is on the left, you see the gravity-only simulations that Kelly just talked about. And from the right, you see observational data. And in the middle, you see the measurement of the correlation function. So red dotted line is if you just take the gravity-only simulations and you measure the correlation function and you do the emulation part that Kelly described. And what you see, if you compare it to the black measurement points, which are from the Sloan Digital Sky Survey, which is actually in New Mexico, you see that there's a discrepancy on small scales. So something is missing here. And that something that's missing here is actually the galaxies. So if you would zoom into the simulations, into the gravity-only simulation, and you would zoom in on one of these very bright points there, that's where the galaxies, which you would populate with galaxies. So there's substructure in there. So you can do this now in two ways. So one way is you just put on top of the gravity-only simulation a prescription. You say, like, I know the mass of each of these very halo-like, cluster-like objects, and therefore I know how many galaxies should be in there. I know how old, when these clumps formed, therefore I also know what kind of galaxy should be in there. Like red galaxies are very old galaxies, so if I have a halo that formed very early, I populate it with red galaxies. If I have something that formed very late, I populated it with blue galaxies that are still star forming. So you can find this description. Or what you can do, you can add more physics to the simulation, and you can hope that this physics will capture all of this, and you will form the galaxies in the simulation directly instead of populating it by hand later on. But there's a small problem, and this problem here is scales. So here is an image that I borrowed from the Sky Institute, which is an AI institute that got recently funded by NSF, which is situated here in Chicagoland. And on the left, you see the cosmology simulation that we have talked so far about. And then on the very far right, you see stars. And what you notice is that there is a 20 order of magnitude in space and time in between here, between 10 to the 9 and 10 to the minus 13. So it's totally impossible, even with our wonderful supercomputers that we have today, to do this from first principles, to do these simulations. So what we have to do instead is we have to implement something that is called subgrid models. So I come up with a surrogate models that kind of describes how star formation is working, and put that into my simulations, and I hope that captures all the physics that we want to describe. So Kelly will talk a little bit more about, like, how do we actually tune these models to get this right. But I want to show you a little bit here what these so-called subgrid models actually do to our structure. So in addition to the gravitational interactions that have been what we discussed so far, we now have gas physics. And we have things like, if a region becomes very, very dense, we assume that stars start forming. So we put in star particles, we put in cooling. So we put in all kinds of extra physics that describes what the baryons are going to do. And just to give you a very quick glimpse, so this was the gravity only that we looked at before. And now we add this extra gas physics to it. And so what you see is that the structure actually changes. On top of that, we now put cooling, and you see the effects are actually harder and harder to see. So you see that the small structures are still changing when I walk through these different physical effects. And this is what we want to capture and what we want to compare against observations. This slide kind of, again, sets up a little bit what Kelly is going to talk about, and I give her much more time than I want to pick up here. But what we have done is we have encapsulated the extra physics in our simulation in 5 parameters that describe the astrophysics. So one parameter is galactic outflow. So it's winds that tell us, like, how the gas is coming out of these large structures, energy injection, masses of seed masses of black holes, and accretion rate efficiency of black holes as well. Again, this would be a completely separate talk. The main thing that you should get away from this is take away from this is that we now have, in addition to the cosmology parameters that Kelly discussed in details, she showed you the diagram of these 8 parameters that we varied. We now have also astrophysics parameters that we have to actually calibrate. And here is now just another movie which shows you how this extra physics is evolving in the simulations. So you remember we had first the movie of, again, you have Z here, which is the time variable. So we are going closer and closer to today. And now you have this extra physics. You have a gas temperature, you have gas pressure, and up in the right, you see the stars forming. And as soon as you have enough stars to form a galaxy, we can capture that as well. So this simulation actually provides the direct distribution of the galaxies now. It doesn't force you to put an extra model on top. And so now again, the question is, how do we know how to pick these 5 parameters that are listed here on the right? And that is what Kelly is going to talk to us about next, but let's just finish this movie. So you see here in the right, again, the stars are very important. So you see how you have these clumps of stars that are then forming galaxies. And you can actually follow this in the simulation very nicely and see how close you are to the real universe now. And with that, Kelly will tell us a little bit more about calibration of these subgrid models so that we actually get them right.
Okay, yeah, thanks, Katrin. So Katrin alluded to this, but we have these 5 subgrid parameters that we're going to vary. And in this case, we were just doing kind of one set of simulations. We weren't trying to do this iterative grid filling design thing that we talked about from the last slides. So we just spread them out in the space via Latin hypercube sampling. So we have 5 parameters. We have 64 simulations that attempt to fill the space of these subgrid parameters. The global statistics that we're interested in here, whereas before we were focused on the matter power spectrum, here we're going to be looking at the galaxy stellar mass function, the cluster gas fraction, and the cluster gas density. And we have some observational data sets that give us information about what these things do actually look like in the world. And over on the right, I'm showing the realizations of the simulations for each of these statistics of interest. So on the top, we have the galaxy stellar mass function, middle galaxy gas fraction, bottom cluster gas density. And we have the colors here indicating different values of some of those subgrid parameters. And the points in each case show the observational data set results for each of those statistics. And so of concern would be if our simulations just completely missed the observations. But in this case, we can see we're satisfied with kind of the coverage of our simulation set relative to the observed targets. So now we say, okay, great, it seems like we have run simulations that at least don't totally miss the real world, which is great. And we want to look at how each of these parameters affects these targets. So here the rows are showing each of those 5 subgrid parameters, and the columns are showing the targets. So you can think of this as a way to see how much turning one of these parameter knobs varies a given target. So if we focus on, say, the far bottom left subplot, this would be the change to the galaxy stellar mass function implied by varying this epsilon parameter, and the change is tiny. So it seems that that statistic is not sensitive to that parameter. And of note here is that different statistics have different levels of sort of sensitivity or variability to these parameter changes. So this is going to foreshadow what we're going to talk about later, which is that using them all together gives us more information about what these parameter settings are most likely to be kind of in truth or in these observational data sets. So to get back into the math land here, as we mentioned in the previous slides, eta here is our sort of simulation realizations. Sorry, I mistyped this here. And T are the cosmological parameter settings. So we have our simulator here that has these 64 realizations at these settings T. And our question is, what sort of underlying set of cosmological parameters is likely to have generated our actual observed data? So here, Y is our observed data, and theta is what we want to learn, the cosmology at the observable. And this is where that emulator piece comes in, because we're not rerunning the simulation at every possible set of t-values. We're using an emulator for each of these statistical quantities of interest that we can then just quickly explore the space of thetas to discover kind of what our most likely theta set is. Yeah, and so as mentioned, the parameters here correspond to different sort of underlying physics or astrophysics, but they manifest in the summary stats in different ways. And so what that looks like, if we look at just a single observational target, is that the parameter space isn't very well constrained. So here this is showing two of the parameters and the implied sort of constraint on them by just the galaxy stellar mass function alone. If we look at the red distribution, if we look at the blue, which is kind of tighter, that's if we use galaxy stellar mass and F-gas. And if we look at green, which is even more kind of constrained, even tighter, that's if we add in this last observational target as well. And to look at this in another way, this is the just sort of projected spread of the distribution, posterior distribution of theta. If we're calibrating against a single target, GSMF in red, you can see it's quite wide across the board. So the galaxy stellar mass function alone isn't really allowing us to learn very much about these parameters. Whereas if we incorporate F-gas and the cold gas, then we are able to learn more about kind of where we might want to look closer and run bigger simulations. So yeah, this is kind of that iterative process of saying, great, we have the ability to simulate these or learn these different targets from a given simulation. We have multiple observed data sets, so leveraging all of that information helps us learn more about the astrophysics underlying this situation. And this is just showing the final posteriors for the joint calibration. So the marginals are shown on the diagonal, and the pairwise densities are shown on the off diagonals. And again, this is just saying, look, we have agreement when we use all of these observables together, and we're able to, tighten up on where the most likely sort of space of these parameters lies. And if we use the best fit parameter and look at how that realization of these observables looks for that best fit parameter, that's shown on the right here. There's some weirdness with the CGD values at low R values. And I think that's, again, I'm not a physicist, so I believe from our discussion, this is due to some low cluster counts in our simulation that is resulting in these biases. But I think the sort of like concern there is not that our simulations are wrong, just that we maybe need to run a more expensive simulation with more clusters in it. And when we did that, I'm not showing the results here, but the alignment to the observed target was much better. So that sort of is, reassurance that this is more an artifact of the simulation resolution rather than an issue with the emulator itself or with the learned parameters. Yeah, so the sort of general pipeline here was that we wanted to run a bigger hydrodynamical simulation, so a larger volume, higher resolution simulation, and doing this sort of lower resolution, bigger set of simulations allowed us to get some plausible parameters with which we could do this capstone hydrodynamical simulation and report kind of what the astrophysical behaviors were at our nominal best fit parameters. And yeah, the paper on this hydrodynamic calibration is in the works. We're in the edit phase now. And in the future, our hope is to do calibration jointly with both these astrophysics subgrid models and with the cosmological parameters. And that should involve some interesting statistics. So stay tuned for our next edition of this, maybe next year. Yeah, and we want to make sure to thank the DOE's SciDAC program and also our collaborators who were integral to doing all of this. And I think one or two of them might be online. So hello, collaborators.
Awesome. So thank you to both Kelly and Katrin. I feel like you fit a galaxy of information into a short talk. So we only have 2 minutes left, so I'm kind of hesitant to take any questions at this point. But I will just kind of want to make a plug at this point. I always say that, you know, as statisticians, we get to play in everyone else's sandbox. And here at Los Alamos, we get to play in some really cool sandboxes. And I think this is one of those examples of that. So very grateful to both of you for sharing your work and for participating in this web series. And yeah, thanks to everyone for joining, and we'll see you on May 8th for the next installment. All right, thanks everyone.
Thanks, Emily.
Right.
And thanks everyone for coming.